Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to continue our lecture on light and optics, and we're going to start with discussing refraction. Refraction is the bending of light as it passes from one medium to another and changes speed. This change in speed occurs because light travels at different velocities in different media. For instance, light travels fastest in a vacuum at a speed of approximately 3 × 10⁸ meters per second. However, in any medium other than a vacuum, light's speed is reduced. To quantify this change, we use a value called the index of refraction, which is denoted as lowercase n. This index of refraction is specific to each medium, and it can be calculated using this equation right here. This equation states that the index of refraction is equal to the speed of light in a vacuum divided by the speed of light in the medium. The greater the index of refraction, the slower light moves through the medium. Now, when light moves from one medium to another, for example, from air to water, its direction changes due to this difference in speed. This bending of light at the interface between two media follows Snell's law, which is given right here. This states that n1 sine theta 1 is equal to n2 sine theta 2. n1 and n2 are the indices of refraction for the first and second media, and theta 1 and theta 2 are the angles of incidence and refraction, respectively. Snell's law helps us predict how much light will bend as it enters a new medium. According to Snell's law, if light enters a medium with a higher index of refraction, so n2 is greater than n1, then it's going to bend towards the normal. On the other hand, if light travels into a medium where the index of refraction is smaller, so n1 is greater than n2, then the light will bend away from the normal. Keeping that in mind, let's jump into a practice problem. This example states a penny sits at the bottom of a pool of water at a depth of 3 meters. If an observer 1.8 meters tall stands 30 centimeters away from the edge, how close to the side can the penny be and still be visible? Before we start solving, I want to make note that this problem is mathematically involved, so we're going to be using a calculator. The goal is to ultimately understand how to apply the concepts of refraction that we just covered to a practical application problem. With that being said, the first step is to draw a diagram, which I have right here. So let's work through it. We're given that the depth of the pool is 3 meters. We're told that the observer stands 1.8 meters tall. And we're also told that this observer is standing 30 centimeters away from the edge, which we're going to write as 0.3 meters to match the other units of length. From here, we have to consider that the line of sight that the observer uses to see the penny, it bends at the water surface due to refraction. So here we need to define a few variables. We have theta 1, which is the angle that the light makes with the normal inside the water. And we have theta 2, which is the angle that the light makes with the normal once it exits into the air. From here, we need to identify the line path and angles. The light is coming from the penny at the bottom of the pool, and it travels upwards until it hits the water-air interface. Now, when light moves from one medium to another, especially from a denser to a less dense medium, it changes direction. This change in direction is called refraction. In this case, the light is going from water, which has a refractive index of 1.33, into air, which has a refractive index of approximately 1. We know that air has a lower refractive index because it's less dense than water, meaning that light travels faster in air than it does in water. Since the light moves from a medium of higher refractive index to one with a lower refractive index, it's going to bend away from the normal when it exits the water. This means that theta 2, the angle in the air, is going to be larger than theta 1, which is the angle in the water. From here, we can begin to calculate theta 2. And to do this, we're going to use trigonometry, specifically the tangent function, because what we're dealing with right here is a right triangle. The tangent function is defined as the ratio of the length of the opposite side to the length of the adjacent side of a right triangle. In our case, looking right here, the opposite side is the horizontal distance from the observer to the edge of the pool, which is equal to 0.3 meters. And the adjacent side is the vertical height of the observer's eye level above the water, which is equal to 1.8 meters. So here we have tangent theta 2 is equal to 0.3 meters divided by 1.8 meters. And if we plug this into a calculator, this fraction, we get 0.167. So tangent theta 2 is equal to 0.167. Now to solve for theta 2, we take the inverse tangent of 0.167. So theta 2 is equal to inverse tangent 0.167. Plugging this into a calculator, we get approximately 9.5 degrees. From here, we can use Snell's law to solve for theta 1. So Snell's law is a formula that relates the angles of incidence and refraction to the refractive indices of the two media. So as a friendly reminder, Snell's law is N1 sine theta 1. This is equal to N2 sine theta 2. And our goal is to solve for theta 1. So the first thing we'll do is divide both sides by N1 so that we get sine theta 1 is equal to N2 divided by N1 sine theta 2. N1 is the refractive index of water, which is equal to 1.33. N2 is the refractive index of air, which is approximately 1. Theta 1 is the angle of incidence in the water. That's what we're trying to calculate. And theta 2 is the angle of refraction in the air, which we just calculated as 9.5. So let's plug these values in. We have 1 over 1.33 sine 9.5. If we plug this into a calculator, we get that sine theta 1 is equal to 0.124. We can now take the inverse sine to find theta 1. Theta 1 is equal to the inverse sine of 0.124, and this is equal to approximately 7.1 degrees. Now we can move into our final step, which is calculating x. We need to find the horizontal distance x from the point directly under the observer to the penny at the bottom of the pool. This distance will tell us how far from the edge the penny can be for the observer to still see it. Since we know theta 1, we just calculated that, and we also know the depth of the pool, which is equal to 3 meters. Once again, we can use our tangent function to solve for x. Tangent theta 1 is going to be equal to opposite divided by adjacent. Opposite is x, that's what we're trying to solve, Adjacent is the depth of the pool, which is equal to 3 meters, and theta 1 we just calculated is equal to 7.1 degrees. Now all we have to do is rearrange this expression to solve for x. X is equal to 3 meters multiplied by tangent 7.1. And when we plug this into a calculator, we get 0.37 meters, which is equal to 37 centimeters. So the penny can be up to 37 centimeters away from the edge of the pool and still be visible to the observer that's standing 30 centimeters away from the edge. And with that, we've completed this problem, and we can move into our next topic, which is total internal reflection. An interesting consequence of refraction is the concept of critical angle. When light travels from a medium with a higher index of refraction to one with a lower index of refraction, for example, from water to air like we saw in our practice problem, there is a specific angle of incidence at which the refracted ray skims along the boundary between the two media. This is known as the critical angle. When the angle of incidence is exactly equal to the critical angle, the refracted ray travels along the surface, creating a boundary effect without penetrating into the second medium. If the angle of incidence exceeds this critical angle, then we observe a phenomenon called total internal reflection. In this case, all of the light is reflected back into the original medium, and none of it refracts into the second medium. Total internal reflection is particularly important in applications like fiber optics and certain optical instruments where controlling the path of light is super essential. The critical angle, it can be calculated using this formula right here. This formula says that the critical angle is equal to the inverse sine of n2 divided by n1, where n1 is the index of refraction of the initial higher index medium, and n2 is the index of the second lower index medium. With that, we want to move on to lenses and see how they differ from mirrors in terms of image formation. Unlike mirrors, which reflect light, lenses work by refracting light. When light passes through lenses, it encounters two surfaces. It refracts once as it enters the lens from air, and again as it exits the lenses back into air. This double refraction alters the light's path, and it enables lenses to focus or spread out light rays, creating images. We're going to start with first discussing thin spherical lenses. These lenses have two focal points, one on each side due to their symmetry. Thin spherical lenses follow the same fundamental equations that we've seen with mirrors for determining image distance and magnification. The equation for image distance in lenses is given here. We have 1 over f, which is the focal length. That's equal to 1 over o, which is the object distance, plus 1 over I, where I is the image distance. This equation helps us calculate where an image will form based on the lens focal length and the position of the object. For magnification, we also use the same formula as we did with mirrors. Magnification is equal to negative I divided by O. In lenses, a positive magnification value indicates that the image is upright, while a negative value indicates that the image is inverted. Now that we've discussed thin spherical lenses, let's move on to real lenses. These are lenses in which the thickness cannot be ignored. For these lenses, the focal length isn't simply a fixed property, but instead it's influenced by the curvature of each surface and the material's refractive index. The focal length of a real lens can be determined using the lens maker equation, which you see here. This equation says 1 over the focal length is equal to n minus 1, where n is the index of refraction of the lens material, and that is multiplied by 1 over R1 minus 1 over R2. Here, R1 and R2 are the radii of curvature for the two surfaces of the lens. Having a positive value of R indicates that the surfaces curve outward, so it's convex, and a negative R value indicates an inward curve, so it's concave. Now, the lens maker equation is really crucial in optical design because it allows us to calculate the focal length based on the material and shape of the lens, and that makes it useful for lenses with significant thickness. To further clarify the behavior of real lenses, let's take a look at the sign conventions for lenses. We're going to start with object distance. A positive object distance indicates that the object is on the same side of the lens as the light source. A negative object distance suggests that the object is on the opposite side of the light source. What about for image distance? A positive image distance indicates that the image is formed on the opposite side of the lens from the light source, making it a real image. A negative image distance means that the image appears on the same side as the light source, and that indicates that it is a virtual image. Now let's consider radius of curvature and focal length at the same time. For convex or converging lenses, both the radius of curvature and the focal length are positive. For concave or diverging lenses, these values are negative because the lens diverges light rather than focusing it. Finally, for magnification, a positive magnification value means that the image is upright, while a negative magnification indicates that the image is inverted. To add to this, lens power is another important property, especially in corrective lenses. Lens power is denoted as capital P. It is the inverse of the focal length, and it's measured in diopters. The power of a lens is given as 1 over F, and F is measured in meters. Now, a positive power indicates a converging lens, so convex, while a negative power indicates a diverging lens, so concave. And this measurement is really useful in optometry, where lenses are prescribed based on the amount of correction needed to focus light onto the retina. With that, let's discuss multiple lens systems. When we say multiple lens system, we're discussing two or more lenses that are used in close proximity. When lenses are in contact or have negligible distances between them, they work together as a single combined system with an equivalent focal length, power, and magnification. For each system, the equivalent focal length is calculated using this equation right here. F1, F2, F3, and so on represent the focal lengths of each individual lens. So this equation allows us to determine the effective focal length of the entire system, which behaves as if it were a single lens. Similarly, the power of the combined lens system is the sum of the individual powers of each lens. Power is measured in diopters, and this additive property makes it easy to calculate the overall power of the system based on the strengths of the individual lenses. For magnification for a multiple lens system, this is going to be the product of the magnifications produced by each lens. So by multiplying the magnifications, we can find the total magnification of the system, which tells us the overall size of the image relative to the object. Now, it's important to note that multiple lens systems, like single lenses, are not without imperfections. Aberrations are a common issue in both lenses and mirrors that cause image distortion. There are two main types of aberrations that we should be aware of: spherical aberrations and chromatic aberrations. For spherical aberrations, this occurs when light rays passing through the edges of a lens or mirror are not focused at the same point as rays passing through the center. This mismatch leads to a blurred or distorted image. For chromatic aberrations, this type of aberration is due to the dispersion of light. Different wavelengths of light refract at slightly different angles when passing through a lens, and that results in colored fringes around images. Now, we've covered everything we needed to for Objective 2. We can move into Objective 3 and begin to discuss diffraction. Diffraction is the phenomenon where light spreads out when it passes through a narrow opening or around an obstacle. This spreading effect is due to the wave nature of light. When light waves pass through a slit, they don't just continue in a straight line. Instead, they spread out in various directions. So for a single slit diffraction, this specifically occurs when light passes through a single narrow opening. In this case, light waves fan out or diffract from the edges of the slit. If the width of the slit is on the same order of magnitude as the wavelength of light, then the diffraction effect is more pronounced. If the slit becomes more narrow, the light spreads out even more widely, and this spreading results in a pattern of bright and dark areas. When a lens is placed between a slit and a screen, it focuses the diffracted light waves, and it creates a visible pattern of alternating dark and bright areas on the screen. This pattern is known as a fringe pattern, and the central bright area is called the central maximum. It's typically the widest and most intense part of this pattern. Now, as the slit width becomes smaller, the central maximum becomes wider, and the spacing between dark and bright fringes changes. The formula you see here helps us determine the angles where dark fringes will appear. Dark fringes are areas of destructive interference. This formula says A sine theta is equal to n lambda. A is the width of the slit. Theta is the angle from the center of the slit to a point of minimum intensity on the screen. N is the integer representing the order of the dark fringe, and lambda is the wavelength of the incident light. To reiterate, this equation indicates that dark fringes occur at specific angles depending on the slit width and the wavelength of light. Bright fringes appear in between these dark fringes. From here, we want to discuss what happens when there are multiple slits. This also brings up the concept of interference. Interference happens when multiple waves overlap, adding their effects together. In Young's double-slit experiment, light passes through two closely spaced slits, producing two sets of overlapping diffracted waves. When these diffracted waves meet on a screen, they interfere with each other. When waves meet in phase and their peaks align, they amplify each other, creating bright areas called maxima. This is called constructive interference. When waves meet out of phase, so one peak aligns with another's trough, they cancel each other out, creating these dark areas called minima, and this is known as destructive interference. This alternating pattern of bright and dark regions on the screen reveals the wave nature of light, and the positions of these dark fringes can be calculated using this formula right here. D sine theta is equal to n plus 1/2 multiplied by lambda. D is the distance between the two slits. Theta is the angle of the dark fringe from the central axis. N is the integer representing the fringe order, and lambda is the wavelength of light. This equation shows that dark fringes occur at specific angles, with bright fringes appearing between them. Now, building on our understanding of diffraction and interference, we should talk about diffraction gratings. Diffraction gratings take this concept further by using multiple slits arranged in a regular pattern. When light passes through these diffraction gratings, each wavelength or color of light interferes with itself and other wavelengths in a distinct way, and it creates colorful patterns. This effect is similar to how a prism disperses light, but instead of bending light by refraction, diffraction gratings separate colors through interference. And with that, we can move into our final objective, where we can discuss polarization. Polarization refers to the orientation of light's electric field. Unpolarized light, such as light emitted from most natural sources, consists of waves with electric fields oscillating in all directions perpendicular to the direction of travel. Polarization restricts the orientation of these electric fields, creating different types of polarized light. Let's start with discussing plane polarized light. In plane polarized light, the electric fields of all the waves are aligned in the same direction. This means that rather than oscillating in multiple planes, the electric fields in plane polarized light are confined to a single plane perpendicular to the direction of propagation. To achieve this effect, light can pass through a polarizing filter, which only allows waves with electric fields oriented in a specific direction to pass through. For example, after passing through a vertically oriented polarizing filter, only the vertical components of the electric field will remain, and the light becomes vertically polarized. This type of polarization has practical applications, such as in sunglasses and camera lenses, which use polarizing filters to reduce glare by blocking specific orientations of light that are commonly reflected from surfaces. What about circularly polarized light? This is another type of polarized light, but it differs from plane polarized light in how its electric field behaves. In circular polarization, the electric field has a constant amplitude, but it is continuously changing direction in a circular or helical pattern as the wave propagates. This effect is created by combining two plane polarized waves that are perpendicular to each other, but out of phase by a quarter wavelength, so 90 degrees. As a result, the electric field vector appears to rotate, creating this helical shape along the direction of travel. Circular polarization is commonly used in optical devices and technologies like 3D movies, where circularly polarized light allows each eye to receive a different image through polarizing glasses, creating this really unique effect. In summary, polarization is a property that restricts the orientation of light's electric field, resulting in different types of polarized light. And with that, we've completed our chapter on lights and optics. I hope that this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.